This video will cover section 2 of chapter 8. Our focus will be on determining the required sample size for estimating a single population mean and that confidence interval. There are three conflicting objectives. We'd like to have a high confidence interval, but remember, a higher confidence level means a larger margin of error and a wider interval. We'd like to have a low margin of error for the same level of confidence, because a low margin of error means that our interval is narrower and more precise. And we'd like to have a small sample size because a small sample is more cost-effective and saves us time. For a given sample size, a high confidence level will tend to generate a large margin of error. For a given confidence level, a small sample size will result in an increased margin of error. Reducing the margin of error requires us to either reduce the confidence level or increase the sample size, or both. So you see there are trade-offs between those three things. The focus of this section of the book then is to help us figure out how to get an approximate sample size to reach our desired margin of error and level of confidence. So remember from the last section, when we were calculating confidence intervals, the whole right-hand side of the plus or minus was the margin of error. The margin of error is the critical value times the standard error. The formula for calculating the required sample size actually just involves solving for n in the margin of error equation. So to calculate the required sample size, assuming we know the true sigma, we would take z times sigma, our critical value, times sigma, divide by e, that's our desired margin of error, and square all of that. Or you can square each of those components. So an example, if sigma is 45, our population standard deviation is 45, what sample size would we need to get to be 90% confident of being within plus or minus 5? So the sigma's easy. We see what that is. That goes right in where the sigma is. We need to be 90% confident, so we would go to the z table or norm inverse and find that 90% confident means a z critical value of 1.645. And we want to be within plus or minus 5. So our margin of error, or our E, is 5. Plug that all in, multiply some stuff out, and simplify. We get 219.19. We always round up. So to meet this 90% level of confidence, and only 5 units for the margin of error, we need to have 220 items in our sample. So what if we don't know sigma? Well, we'll have to use our best guess for that. So there are a couple of ways to do that. One of the ways is to pick a value that you think would be at least as large as the true standard deviation, and just plug that in and use that. Another method would be to select a pilot sample. That means get some responses from some of the people in the population of interest, and calculate the sample standard deviation, or S, from that sample. And then we could use S in place of sigma. Suppose that we have no way of estimating the true population standard deviation, either by a rough estimate or by doing a pilot sample. We could instead then take the range, which would be the difference between the biggest value we expect and the smallest value we expect, and divide that by 6. If we want a really conservative estimate, in other words, we want to produce a larger sample size just to be sure that we're getting the margin of error that we want, we actually choose the range divided by 4 instead of divided by 6. So that's for a conservative estimate. You know it's going to give you a larger sample size. So we'll use an example here for the case where we don't know the true population standard deviation. Suppose we're interested in finding the sample size needed to be very conservative and to have a 95% level of confidence of being correct within plus or minus 10. Suppose that we believe the range of the data is 1400. So we're going to take 1400 and divide it by 4 because we want that conservative estimate. That gives us an estimate for the standard deviation of 350. Because it's a 95% level of confidence, we use the z critical value of 1.96. So 1.96 squared, 350 squared, divided by the margin of error 10 squared, we get 4,705.96. So the required sample size is 4,706 items.